Okay, let's start our discussion for this session. We are at page 94. Those who have textbooks are advised to take the textbook, and maybe you want to take some notes. We are at chapter 4, deterministic signals. Okay, so in the previous chapters, when we talk about a signal model, recall what we do. We always say, hey, there is a signal that is A, that is a constant A, or there is a minus A, or there is something like 0. Recall in chapter 3, right? We always do something like that. Now, here, as an example, I think let me show you some examples so as to make some connections between the chapters. You see, in this page 83, we are talking about minus a, which is a constant, right? And here it's 0, here's a, and those things, you start to wonder, where is the time? Where is the time index? Right? 你会好奇说，这个讯号的模型看起来很抽象，因为 A 那为什么没有时间？我们在通讯不都是有时间吗？时间轴跑哪里去了？对不对？这个的确是个问题，所以这是个简化的模型。然后我们会越来越接近实物的去探讨它。So at chapter 4, we start to see there will be time index coming in. Will be time index coming in. Right? It's no longer just an abstract number A. We're starting to have time index. Okay. Again, page 94. Okay, so it's a detection of an unknown signal in Gaussian noise. Usually we have Gaussian noise. That has not changed. But this is the simplest detection problem encountered because the resultant hypothesis is a simple versus simple hypothesis. As discussed in chapter 3, optimal test is well known. If the probability of detection is to be maximized subject to a constant probability of false alarm, then that's Neyman-Pearson. Or to minimize the average cost, that is the Bayesian risk, right? Bayesian. That is a Bayesian. Furthermore, the resulting test statistic is a linear function of the data due to the Gaussian noise assumption. Therefore, the performance of the detector is easy. I would say it's not that easy, but in the area of detection and estimation, that is easy. But if this occurs for the first time learning this, you may not consider easy, but uh, try to read more papers on detection, you will find that question, that problem is actually simple than most engineering problems in practice. The detector that evolves from those assumptions is termed the match filter. That is the key point in this chapter. Then it has extensive use in applications in which the signal is under the designer's control so that the unknown signal assumption is valid. The example is, of course, the coherent communication systems. Right, so this is just a summary of the sections. We'll talk about MRE and the some of the correlator structure. And yeah. Okay, so we will go into the match filter discussion. The development of detector. We begin our discussion of optimal detector approach by considering the problem of detecting a non-deterministic signal. Uh, I want to clarify this non. Usually, when we talk about signal model, we have some kind of description about it, and there could be many, many different ways of describing a signal model, and there could be many types of signal model. But here we are talking about known and deterministic. And among those, we could have unknown deterministic, right? As you know, if there is something known, then there is something unknown. If there is a deterministic, then there is what? There is stochastic. There will be stochastic version of it, right? So uh, there could be different versions of the signal model. That's a point. But here we are dealing with the simple one, which is known and deterministic. So next time when you see a paper or you see something, people are talking about different types of signal, you should know that there could be such cases. And then the Neyman-Pearson criteria will be used, but as discussed in Chapter 3, the resulting test statistic will be identical to that obtained using Bayesian risk. Okay, the detection problem is to distinguish between the two hypotheses. What two hypotheses? One is H0 without signal, and then there's a noise. And the other is H1 with the signal S, but that signal S is let's just call it S for now, and we'll describe its characteristics later, and with a noise. Where the point comes here is assumed known. The Sn is assumed known, and Wm is white Gaussian noise with variance sigma squared. Then of course, as I say now, the time index comes in. How come? Because you have Sn, then that S is no longer a constant. Recall previously what we talked about is about a signal that's called A, and A is a constant without any relationship with the time index. Now we have a Sn, and that Sn is sort of a sampled version of a continuous signal. Another word, uh, a sampled version of a continuous signal. So now we have Sn n from 0, 1 all the way to n minus 1。你可以把 Sn 想成是一个连续讯号，然后在这些离散的点被 sample 出来的一个离散版本的讯号，这样。实物上你可以这么想，但是在这里呢，当我们 sample 完之后，它就变成 S square bracket of n。Then WGN is defined as a zero mean Gaussian process with autocorrelation function sigma square this sigma square delta k, right? Of course, this autocorrelation function is the expectation of a process with itself, but that processes with itself within a certain time distance, meaning that this is n, then it's at time index n plus k, and then you take the expectation. So if you're not familiar with this ACF, then you recall the random process that you may have learned. But if you have not learned about random process, then please just try to find out some tutorials of ACF and try to just get a little bit understanding of it. It'll be easier to understand this. So this is a discrete time delta function, delta function. Then the delta function is equal to 1 if k is 0. Then delta function is 0 for k not equal to 0. I think this is just a mathematical definition. If you recall 讯号与系统 signals and systems in undergrad class, we have this delta function, right? So it's the mathematical definition. And such a model can be derived from a continuous time set that was described in some pages, but it doesn't matter. Just think of it as a sampled version of a continuous signal，就是把它想成是你有一个 continuous signal，它是长成 s of t，然后在 n 等于0、n 等于1、n 等于到 n 减1的这些点被取了 sample，所以变成离散的版本，就这样子想，就可以理解它了。好。Then the NP detector will decide H1 if the likelihood ratio exceeds the threshold. So the L of x will be equal to P of x larger than gamma. Where we have this. And then here comes the same technique. Here comes the same technique. What technique? It is in fact you think of it as this, we have no problem with this, right? Because it's Gaussian. So we don't have problem with this guy. It's a zero mean Gaussian. We're fine with it. We're fine. But we have a little bit of problem with this, right? Because it's like you have different value for different n. Now, think of it as a multivariate Gaussian. So when you are calculating p of x condition on h1, you have something like this, then exponent of something like this. But this is what? Think of it as mean s, and then it's disturbed by Gaussian random variable w. Remember this keyword. We are talking about deterministic s. So that s can be treated as what? As constants. Therefore, this s is like a mean in this whole random variable. So you see its role here is like a mean， 就是它的角色在这个 PDF 里面就变成像是 mean 一样的。因为我稍微讲慢一点，然后让大家可以跟得上，因为这个部分很重要，然后又看起来写起来虽然很简单的，但是它的观念其实是很重要的。就是说，为什么我们一开始在这里讲它是 non-deterministic？如果我们说它是 non-stochastic， 我们就不能这样写了，因为 S 就会变成是 random variable 了。可是在这里我们说它是 deterministic 的意思就是它在这里可以被当成常数，只是每一个 n 所对应的 s 的常数不一样，这样。所以你如果这样去理解它，你就会发现 s 它是一个常数，只是它的值不一样，随着 n 会不一样，所以它就变成Gaussian random variable 的 mean， 但是每一个 n 都不一样。你这样去理解它，哦，那你就可以理解 this equation looks like a Gaussian distribution with different mean, which is the s with different n. Okay, then that'll be easier, right? That'll be easier. Okay, so now we talk about NP detector. We talk about Bayesian detector, right? We talk about base risk with costs associated with each decisions, right? Those are in chapter 3. Now, we like to first do the NP detector for this one. So the NP detector decides H1 if the likelihood ratio exceeds the threshold, or we will say L of x equal to something like this, right? This is always the general rule meaning that it applies to many different settings. So we will still use the likelihood ratio test, except the difference is when you are writing the probability density function, it will be different with different signal model. But here, it, as I explained, it's a Gaussian distribution with different S. Then you do this divided by this, which is here, right? Which is the likelihood ratio. Then we have L of x equal to something like this. This is multivariate Gaussian, and so you cancel out a lot of things like the sigma square of to the n over 2, things like that. You cancel it out, and then you simplify it. This is sort of like a manipulation, mathematical manipulation. Then you get the whole thing like this. You have what? You have exponent in it. Still have this Sn in it. Then you have samples in it, right? Which are all reasonable. Why? Why is it reasonable? Your information comes from what? Comes from samples X. And you need the information of your deterministic signal S to make decisions. So this whole thing is intuitively reasonable. Then larger than a threshold gamma. Okay, so now we come to page 96. 96. So by this equation, by this equation, we follows and then take logarithm of it, which is again a monotonic function of both sides, and it does not change the inequality, so that you take log likelihood ratio. Log likelihood ratio becomes like this and larger than ln gamma. Then we will decide h1 if this thing is larger than ln gamma, right? Let's take a detailed look. This is monotonic, so when you take ln, it doesn't matter, right? It doesn't matter. Well, in fact, sigma square is known, and in an inequality, a constant exists here. It doesn't really matter, right? Because if you multiply this sigma square up to here, it would be sustained. The inequality still sustains, so it doesn't matter. And then Sn is known, and another function of the data. We incorporate the energy turn into a threshold to yield what? See this. This part is what? This is known. S is known. So you put it at the right hand side. It's good, right? We're good with that. And then there is sigma square. As I said, sigma square can be multiplied to the right hand side. So again, this is again a mathematical manipulation, but it's simple. You put this at the right hand side, you put sigma square at the right hand side, but of course you do it correctly in a mathematically reasonable way, then you get something like this. Let's just not look at this t first. Let's look at this first. This comes from the way I just said. You put this at the right hand side, you put sigma squared at the right hand side, and you get something like that. Okay. So now we have this larger than that. This is equivalent to this. Okay. So now you have this t of x equal to something like that. In fact, we should say it this way. We should say we first get this inequality, and then we denote. It's our notation. It's not mathematical derivation. It's our notation. Our notation to make this equal to t of x. So t of x is by our own notation, artificial. Okay. 就是这个 T of X 是我们自己去把它定义出来的，它不是说导出来的，它并不是，是这一项这个 X summation 这一项是导出来的，没有错。可是我们把它后来用 notation 定义成 T of X，为了方便表达，并不是说我们推导而去导出 T of X，并不是的。OK，to clarify, just want you to be clear about this. And then you call the right hand side of the inequality a new threshold. A new threshold. The whole thing is called a new threshold. 就是把这一整串东西弄成一个 gamma prime，因为既然 gamma 是要被算的，然后它又隐含了一堆已知的常数啊，为了不那么复杂，我们就把它定义成，把它重写成一个叫 gamma prime 的东西，没什么大不了，这就只是变数重新定义一下而已，哦，没有什么大不了的定义这样。OK，then we decide then this whole thing will be mathematically in a more simple form, which is we decide h1 if t of x this which is this larger than this which is gamma prime. Okay, then gamma prime. So this is our NP detector as expected. Consists of a test statistic t of x, a function of the data, and a threshold gamma, which is chosen to satisfy PFA equal to alpha for given alpha. And then we are going to have an example. But for this week, for this class, we'll just go up to here